Hey guys, so in this class we are gonna take a look at debug. We'll actually be introduced to debuggers. Okay, so our objectives here are do an overview of debugger types. Obviously, we first need to understand what debuggers are. Then we'll understand the different types of debuggers. We'll also learn how to differentiate kernel mode and user mode malwares and kernel mode and user mode debugging. Then we'll take a look at how to compare or how to differentiate kernel and the operating system. Actually, this is you really need to understand what a kernel is and what the operating system is. You need to understand the difference, and you actually see that basically there is roughly no difference between a kernel and the operating system itself. But there is a small difference, and we'll talk about that. We'll also talk about the differences between debuggers and disassemblers, and we'll understand what breakpoints are and the different types of breakpoints. Okay, so as you know, so far this is what we have done. Actually, we did not talk about the CyberChef tool. Okay, this is something that we'll talk about in our next class. So far, right, we completed all the basic static analysis. We looked at all the basic static analysis. We looked at the advanced static analysis as well by learning how to use disassembly tools such as IDEPRO and Ghidra. We talked about C programming, C coding, right? We covered some assembling programming foundation, covered some Windows programming foundation. Specifically, we talked about Windows APIs and dynamic shared libraries and Windows functions. Like I said, we did not talk about the CyberChef tool. That's something that we're going to do in our next class. And we actually completed so far 5 labs. So labs 2, 3, 4, 5, and 6, right? Okay, so what are we going to cover here? We're going to take a look at the X32DBG debugger, and we're going to do that in order to learn what the basic dynamic analysis steps as far as debugging, as far as advanced debugging or advanced dynamic analysis, right? We'll also focus on the advanced dynamic steps, including debugging of DLL malware, anti-debugging techniques. Obviously, this is not something that we're going to see in this class, but next week. Covered behavior of different malware type, cover analysis of packed malware. We'll see how we can solve labs 7 and 9. And obviously, we are not going to, there is no module 3 exam, only module 4 exam. So we are going to address that. Obviously, again, not in this class, but what we are going to study from now on is the object of the third exam, which is the module 4 exam. Okay. So in this lecture, the topics that we are going to cover are overview of debugger types, kernel mode versus user mode malware, and all those other topics that I already mentioned, right? So first of all, source level debuggers. Source level debugger are usually built into integrated development platform, and it operates on the source code. You can also set breakpoints, right, as you are analyzing the code, and you can step through program one line at a time. So an example is whenever you're using the Visual Studio debugger feature from Visual Studio, You could also use the GNU debugger GDB to do that as well. But in summary, a source level debugger is a debugger that you can use in order to when you have access to the source code of that application. And the source code meaning the code, the source file that has the source code in which the application was written. So let's say if it's an application that was written in C language, right? So if you do have access to the C code, then you can perform a step-by-step analysis of that code as you execute the code. And that is what a debugger is. Now, it doesn't matter if it's a source level debugger or a real-time or an assembly debugger. Just generally speaking, debuggers are tools that allow you to inspect, to follow up what's going on during the execution of that application. Okay? So imagine that you are executing, you're running a browser, right? You're using your Chrome browser, for example. Let's say that you want to observe the exchange of data while you are using that browser. So when you open the browser and you type, let's say, psu.edu and you hit enter, what happens after you hit enter? If you want to observe all the data that is being generated and transmitted during that communication, you can use a debugger to do that. Okay? Now the difference here is a source level debugger is a debugger that requires you to have access to the source code of that application. Okay? Whereas an assembly level debugger, that's what we are going to do. When you do not have access to the source code, but you do have access to the application itself, okay? Only the, for example, the executable file, the .exe file, or the resulting, it doesn't matter what extension the file is, but you only have access to the executable file, so you don't have access to the source code. Then one thing that you can do, one type of debug that you can run is an assembly level debugger. Okay? So assembly level debuggers, they are low level, they are more powerful because you operate on the assembly code rather than the source code. You can step through the program one instruction at a time. You can examine memory locations, and we're going to see how that's done. So at this point, we've talked about registers and memory addresses many times, right? So how can you inspect the data, the values that are stored in the register during the execution of an application? How can you retrieve the data that is stored in the memory, in the RAM or in the main memory during the execution of that application? You can use assembly level debuggers to do that. Also, you can set breakpoints, and the breakpoint is nothing more than a resource that will allow you to force the application to stop at that specific location. Okay? Now, this specific location can be an assembly line, okay, when a specific assembly instruction is found, or when a specific memory address is used. So there are different types of breakpoints that you can assign. Malware analysts make heavy use of assembly level debuggers because obviously we as malware analysts, we do not have access to the source code. Right? Some examples of assembly level debuggers are OLI-DBG, X64-DBG, X32-DBG, the GNU DB or GDB, as you saw, right? It is a source level debugger, but also an assembly level debugger, and there is also WinDBG. Personally, I believe that X32DBG and OllyDBG are the best ones because they are more, let's say, friendly, user-friendly. Okay. GNU DBG, the GNU Debugger GDB, is probably the most powerful one, but it's used in the command line, so as you can imagine, it is not the most friendly one. Okay? Okay, now we got to understand the differences between debugging in the user mode and debugging in the kernel mode. Okay? So user mode, that's when the debugger is running on the same system as the code being analyzed. So you are debugging, you're going to do that when you're debugging a single executable, and it's separated from other executables by the operating system itself. Whereas the kernel mode requires two computers because there is one kernel per computer. So if the kernel is at a breakpoint, the system stops. So in summary, the difference is, let's just jump ahead and understand the difference between, okay, so let's address kernel and operating systems. Okay, so the kernel is the heart of the operating system that controls and manages access to system resources. Okay, so what that means is the kernel is responsible for enabling multiple applications to effectively share the hardware by controlling access to the CPU, memory, disk I/O, and networking. Okay, so what that means is if you think about if you think about how an application works. Okay, so again, let's go back to the browser example. Let's say that you're going to use your browser. Okay, so you launch that application, and ideally that application is going to access it will need to use or communicate with a few hardware components, such as your display, or your monitor, your graphical interface card, and also your network interface card, right? Now imagine if a application could directly communicate with those hardware components. That could be severely harmful, right? For example, you install an application and you don't know where it came from, but you think that you can rely on it. And let's say that this application could directly send an instruction to your network interface card. Well, obviously, if that application is not well coded, or if the person that wrote that application intentionally included some lines of code there to damage your network interface card, then the application could do just that. That's one of the reasons why we have the operating system. So the operating system is nothing more than an interface between the applications that you're using and the hardware components. Okay? So the operating system is there to control how the applications are interacting with the hardware components, to filter what is being sent to the hardware components, such as CPU, memory, disk I/O, networking, etc. Okay? Now, what is the difference between the kernel and the operating system? Well, actually, the kernel is what I just explained. The difference between the kernel and the operating system is that the operating system is the kernel plus the applications that are provided to you. So that's why I said that roughly there is no difference between the operating system and the kernel, because they are the same thing. But when you get the kernel and you attach or you include a few applications and release that software, again, the combination of kernel plus a few other applications, the name that you give to it is operating system. Okay? So, with that in mind, understanding that the kernel is the operating system itself, and it's there to control what you do, what the applications are achieving, what the applications are requesting, are sending, right? Now we can go back here to understand the difference between user mode and kernel mode. So, considering that kernel is the core of the operating system and it's controlling everything that is done, right? The way that the applications are requesting or sending data to the hardware components. Well, the kernel mode, considering that the kernel is the operating system itself, if you want to debug the kernel, debugging means that you're going to inspect the actions, you're going to inspect the values, the data that is being offered or used or provided by that application. So if you are debugging an application, but this application is the operating system itself, because the operating system is the kernel, you won't be able to use the operating system. That is why kernel mode debugging requires two computers. One that is going to be the computer to be analyzed, and the other one that is running the debugger. Which means that this is not what we're going to do. We're going to do user mode debugging. Okay? That's the kind of debugging that you need to use when you are debugging an application, a specific application. Okay? So, now, with that being said, we can also differentiate user mode malware or user mode applications and kernel mode malware or kernel mode applications, generally speaking. Okay? Again, if we consider that the kernel is the core of the operating system, right? If you see an application or a malware that is a kernel application or a kernel malware, that means that application is directly interacting with the hardware, or at least it is capable of sending instructions to very important system drivers or system libraries that are going to interact with the hardware. Again, it's very, very difficult to write this kind of malware. That is why the most common type of malware that are out there are the user mode malware. A user mode malware is nothing more than a user mode application. It's just an application, okay? But with the intention of doing something harmful, okay? But observe that here you have the malicious program, right? Or your malware. That malware is using dynamic libraries, right? Provided by the operating system, such as kernel 32, NT-DLL, and so many others that are provided by the operating systems. Now, again, if you remember, if these are libraries provided by the operating system, whatever comes from the malicious code, the malicious application, it is going to be filtered by the operating system. So that's why malicious code, malware, when they are user mode malware, they are not going to harm your hardware. Okay? So they can steal file, they can install a backdoor, they can they can cipher a file, but they are not going to directly affect your hardware. Okay? And like I said, since this is the most common type, that's what we're going to focus on. Okay? So, obviously, setting up kernel debugging might be interesting. That is why I included these slides here, but that is not something that we're going to spend much time. You just got to remember that's something that you do. In order to do that, you need two separate machines. Okay? So, user mode assembly level debuggers, that's what matters to us. So assembly level debuggers, they are low level, they are more powerful when compared to the source code debuggers. Okay, they operate on assembly code rather than source code. You can step through the program one instruction at a time. Actually, this depends on whether you want to do that or not. Okay, so you can do a step-by-step debugging, which means you go line by line in observing the values that are being sent to the registers and to the memory locations according to each line all the way to the end of the application. Obviously, this is not very productive. Or you can do something that we're going to see, which is creating breakpoints. Okay, so that's what we're going to focus more, which is setting breakpoints. Okay. Now, obviously, we need to be able to differentiate debugger and disassembler, right? A disassembler, as we saw, shows the state of the program just before execution begins, because you got to remember what we're doing when we're using a disassembler is we're basically just reverse engineering the code, right? So there is no execution involved. You're just analyzing the source code or trying to gather the source code so that you can analyze it, at least in the assembly language. Whereas a debugger provides a dynamic view of a program as it runs during its execution. Okay, so for example, in this example here, a disassembler cannot tell which function is being called. A disassembler doesn't know the content of EAX. Debugger shows the value of EAX. Okay, so in this situation here, if you are using, if you're just using the disassembler, you see the assembly code, right? But for example, what is the value stored in ECX? Well, that's the value. That's the value that is stored in this memory location. Okay, but what is the value? You don't know. Same thing here. What about when you copy the content of EDX into EAX? You don't know what the content is. Same thing here. Call EAX. Okay, but what is the content of EAX? When you're using a debugger, you can identify that. Obviously, the debugger is the tool that will allow you to observe that. Okay, so here in this example, and don't worry, okay, we are not going to do this, and I could be wrong, but I believe that this is the output of the GNU debugger. Oh, okay, this is the Win debugger. Okay, WinDBG. So as you know, we're not going to use GNU debugger or WinDBG. We're going to use a user-friendly X32DBG tool, which is, like I said, much more user-friendly. So, but anyways, observe here that there is a function being invoked, which is create file W, and then there is a bunch of stuff here, and at some point we see here a move operation, move EDI, and then I want to inspect the content of a memory location, and what it shows me is logfile.txt. Observe that logfile.txt is not part of the source code, okay? But I can see it here because I was able to inspect the content, the value, the data stored in a memory location. So the value is stored, the data is stored in the memory location is this file name here, logfile.txt, which you could not do using a disassembler. Okay. Also, another example here, in a situation where you have encrypted data that is going to be transmitted. If a malware handles encrypted data, such as sending encrypted data over a network. You could set a breakpoint where the encryption routine is called to see the data before the encryption routine is applied. So observe here that the encryption routine is invoked right here. So what I could do is I could insert a breakpoint right here, right? At this point, the function, right, the routine, the encryption routine is going to be invoked, but it hasn't been invoked yet. So what I can do is I can set a breakpoint here and then inspect some values, okay, some registers, for example, or memory addresses, probably a memory address, to see the value that is stored in that memory address, and then I would be able to fetch the value before it is actually encrypted. Okay? Okay, now as far as ways of using a debugger, there are basically two ways. You can start the program with the debugger, so it loads the program into the memory. It stops running immediately prior to the execution of its entry point, and it's used to debug malware codes. Okay? You could also attach a debugger to a program that is already running. It is used to debug a program after it has been running. It is useful to debug certain processes that are affected by a malware. I'm sorry. What that means is, first of all, type 1, that is the type of debugger usage that we are going to adopt. Okay, so this is what we're going to do. We are going to use a debugger to launch the application that we want to observe, we want to debug, we want to analyze. Okay? Now, imagine a situation where you have an application, okay, and this application invokes another application. So this other application is already in execution. Okay, it's already been executed, and you want to debug that application that is already running. So you could do this attachment type here. But again, we're going to do this. So basically what we're going to do is, what we're going to learn how to do is, okay, I have this file, I know that this is a malware, and I want to know what it does. We tell the debugger, hey, this is the application that I want to debug. Okay? And what it's going to do is, it will load the application, okay, into the memory, and immediately before the execution of the entry point, okay, it will stop running. It will pause. It will freeze. Okay? And then from there on, you can decide how you want to conduct that debug. Okay? If you want to do it line by line, if you want to, we're going to take a look at the other types that we have. Okay? So, as far as the types, the debugging types, we have single stepping, so run a single instruction at a time and see everything going on within a program. Obviously, this is too time consuming, right? You're never going to do this unless it's a very simple tool or application. What you could do, a situation where you could use single stepping is, okay, you have this application, right? And there is a specific function, there is a specific resource that the application or the malware leverages. And that specific function is what you want to inspect line by line. So you just jump into that function, and then once you enter that function, then you do a step-by-step, line-by-line debugging. Okay, that's basically as far as in a production environment, that's the only situation where you're going to use single stepping. Okay, there is also the stepping into a call function. When you step into a call instruction, the next instruction you see in the debugger is the first instruction of the called function. Then you begin single stepping through the instructions. The advantages is that you understand the task of a certain instruction. Okay, disadvantages, you may step into a function that calls other functions and waste your time. You may step into a function that never returns. In that case, you need to restart the debugger. Okay, now you also have stepping over a function. Okay, oops. So again, stepping into a function is basically when a function is found, then you enter that function and you do a line by line analysis. Stepping over a function, you are going to, well, step over the function, which is different from skipping the function, because when you step over a function, you are not going to enter the lines of code that compose that function, but you are going to get the values, the result of that function. Okay? Whereas when you skip a function, the function is simply going to be skipped, which means that the code will jump from here to here as if that function didn't exist. So if you compare these two types, right, the step over, so you have code, then there is a function call, it is going to step over, which means that the function is going to be executed, okay, and then it will go back to the where the function was and follow to the next instruction. And here the function, it will jump from here to here as if that function never existed. Okay, now the resource, okay, so these are the types of steps that you can use when you're using a debugger. But what we are going to do actually is use breakpoints. Okay, and the breakpoint is nothing more than setting breakpoints, setting locations where you want to pause the code so that you can at that moment observe the content of a register or registers or memory addresses. Okay, so breakpoints are used to pause the execution and allow to examine a program's state. Breakpoints are needed because you can't access registers or memory addresses while a program is running, since these values are changing. Okay? There is also different types of breakpoints. You can use several different types of breakpoints, including software execution, hardware execution, and conditional breakpoints. Depending on the situation, certain breakpoints will not work where others will. Okay, the main difference between software breakpoints and hardware breakpoints and conditional breakpoints. So software breakpoint is a breakpoint that you create, that you establish in your software code. So you have access to the assembly code, right? A debugger will also show you, it is also obviously limited, but it is also a disassembler at some point. Okay, it also shows you the assembly code. So by using a debugger, you can look at your assembly code and say, okay, this is the line, this is the assembly instruction that I want to set a breakpoint. That is a software breakpoint. A hardware breakpoint is a breakpoint that you associates with a hardware information, which means a memory address or a register. So whenever this memory address is used, whether it's the code, the application is retrieving data from that memory address or sending data to that memory address, whatever the case might be, memory address is an address in the memory. The main memory is a hardware component. Register is part of the CPU, which is a hardware component. So that's why they are called hardware breakpoints. And conditional breakpoints are breakpoints that you establish according to a specific condition. So, for example, if a value of a specific register is at some point, the value that is sent to that register is number 5, then it's going to stop, to not stop, but to freeze the execution at that point. Okay? So again, software execution breakpoint, hardware execution breakpoint, and conditional breakpoints. Now, the way that the debuggers differentiate or allow you to use a software breakpoint or a hardware breakpoint, okay, is by using instructions, okay, or hardware registers. But this is not something to worry at this moment, okay? We'll only need this next week when we prepare for Lab 9. Because in Lab 9 we're going to take a look at anti-debugging techniques. So then we'll need to understand how the debugger differentiates software breakpoints and hardware breakpoints. Okay? So that's what we need as far as the concepts before we actually initiate our, learn how to use a debugger, which is something that we're going to do in our next class. Okay? Thank you.